pleasure to listen to Bruno Colbois from University of Neuchâtel, who is going to tell us about upper bounds for the Steklov eigenvalues. So the floor is yours.
Thank you, Laura. So thank you very much for the invitation to your nice seminar, which is so important for our community. It's almost the second year that it takes place. It's very nice. So yes, I will speak about this upper bound for the Steklov eigenvalue, and I will begin by recalling a couple of things that we already hear a lot of times, but it's very important to fix the notation. So I will take a compact connected Riemannian manifold omega, dimension d+1, and the boundary sigma will be of dimension d. And so there is the Dirichlet to Neumann operator. You take a function f on the boundary. You take this harmonic extension h of f, and you tell the normal derivative along the boundary of this harmonic extension, and so it gives to you a new function on the boundary. So we get a pseudo-differential operator between the boundary in itself. Another way to present things is the following. So there is a spectrum first. There is a spectrum which is discrete. The first eigenvalue is 0, corresponding to the constant function. It's possible to find an orthonormal basis of eigenfunction fk of the boundary. And if you take the harmonic extension of this eigenfunction and the boundary, so this harmonic extension satisfies the Steklov problem. The function is harmonic inside the manifold, and its normal derivative is sigma k uk. I will explain some upper bound with coming from geometric methods. So when you try to apply geometric method, it's very useful to have. We use always the Rayleigh quotient. That is, if you have a function in the H1, the Rayleigh quotient is the ratio between the gradient of the function in the whole manifold divided by the L2 norm, but on the boundary. And there is the very classical min-max characterization. That is, if you can get the eigenvalue sigma k by considering you look at all the subspace of H1 of dimension k+1, and when you have one of these subspace, you take the maximum of the Rayleigh quotient for the function on this subspace, and if you take the minimum of the maximum, you get the case eigenvalue. What is important is the following. Of course, it's not the best way to calculate. It's not impossible to calculate explicitly the eigenvalue, but if you take a specific space, what is very important is the following thing. If you take a very specific space here, and if you have an ID, if you can estimate the maximum of the Rayleigh quotient of the function on this space, then you have an upper bound for the case eigenvalue, and this is what we always use. Of course, we have to choose a good subspace of this function. And the last point is there is a Veil law for this eigenvalue, and the Veil law is asymptotically this is k to the power 1 over d, and not 2d as for the Laplacian, divided by the volume of the boundary to the power 1 over d. So my goal today, as I told, is to find upper bound with respect to the geometry of the manifold. So what I mean by geometry, there is of course the geometry of the whole manifold omega, but of course, when you see the definition of the Dirichlet to Neumann, we can think that the boundary will play a specific role. And what is also very important is the position on the boundary inside the manifold. So I will explain about this. By geometry of a manifold, I mean all the classical geometric invariant like the diameter, the volume, the injectivity radius. there is also the curvature, but it's a little specific what concerns the curvature. Let me begin with two very simple examples, but for me very enlightening. The first is the following. You begin with a compact manifold sigma without boundary of dimension d, and as for omega, as a manifold with boundary, you just consider the product. And you denote by lambda 0 less lambda 1 less or equal lambda 2, the Laplace spectrum of sigma. And so there is a relation between the Steklov eigenvalue of the product and the eigenfunction and the eigenvalue of sigma, which go like this. The Steklov spectrum is in fact the union of numbers which depend completely on the spectrum of the Laplacian. This is written there, 0, 2 over L, and then this number square root of lambda k hyperbolic or cotangent hyperbolic of the square root of lambda k times L over 2. I have to say that this is not ordered. You see that, for example, if you take k very large, this will be greater than this number for k equal 1. However, you have the two following things. If you look L going to plus infinity, then the tangent hyperbolic and the cotangent hyperbolic goes to 1. And so approximatively for very large L, you find 2 copies of the square root of the spectrum of sigma. So this is a very simple example, but one sees immediately that there is a very strong relation between the spectrum of the Steklov spectrum of the manifold and the Laplace spectrum of the boundary. So this can be developed. It's not the goal of my talks. It's just to give you a first intuition if you see the problem for the first time. But when you look L going to 0, then if L goes to 0, all this number go tangent of something going to 0, it goes to 0, and the cotangent hyperbolic goes to infinity. So what you know, if you take L very small, it is at the beginning of the spectrum that this is exactly this number, and moreover, they are almost 0. So you lose all information, you have no information, no relation between the Steklov spectrum and the Laplace spectrum of the boundary. So this is a very simple example, but it shows you that the position of the boundary in the manifold is very crucial. Next example. Yes, it's also possible to calculate the eigenfunction for the Steklov in function of the eigenfunction of the Laplace eigenvalue, but it's not crucial for my talks. I wanted to give another example, which is more or less, it has a lot to do. I consider again my cylinder, that is, I take a manifold sigma, compact without boundary. I consider again the cylinder, but I glue to the cylinder, I glue a compact manifold whose geometry and topology may be very complicated. And there is always, of course, it's not possible to calculate exactly the spectrum of the Steklov problem, but the case Steklov eigenvalue is approximated by the square root of the eigenvalue, the case eigenvalue of the boundary. So what is interesting here is that, of course, the geometry near the boundary is very specific. This is a product, but the geometry of this manifold here may be awful. I mean, I can deform it as I wish. It will make some deformation of the sigma k, but you have always this very nice estimate. I have to say that you have here it's very strong because I have only one boundary component. You have the same type of result if you have more than one boundary component, but in this case you have to take into account the spectrum, the union of the spectrum of the different boundary component. And so when you take the union, the eigenvalue 0 has multiplicity. It has the multiplicity of the number of boundary components, so that the first estimate are just sigma k larger or equal. I will begin by giving three very classical results for the spectrum of the Laplacian, because they are much more easy to. And I will give two results at the same time for the Steklov. First, I consider a manifold of dimension n compact connected. The spectrum of the Laplacian is lambda k from 0 to infinity. And first result is a result by Cheng. This is one of the first results in the theory. You make the following hypothesis. You make the hypothesis that you have a lower bound on the Ricci curvature. Under this lower bound, if you have a lower bound for the Ricci curvature, you have an upper bound for the case eigenvalue of the Laplacian with two terms. The first term is more or less a constant, depending on the dimension times the number which gives a lower bound. But then the second term is, of course, depend of the case, the k, but divided by the diameter to the square. So in particular, if the curvature is great, the Ricci is greater or equal 0, you have this nice estimate here. Lambda k less than a constant time k squared divided by the diameter to the square. However, it's not difficult to see that if the curvature is not positive, you need to have a term like this. That is, it's easy to construct. You just take a surface with a long and thin handle, and you have a lot of, you have, the diameter is large, but we have no necessary a small eigenvalue. The next example is of the same type. It is by my advisor, in fact, Peter Buzer, who same type of hypothesis. Ricci curvature is bounded from below, and now this is the estimate is with respect to the volume of the manifold. You see lambda k is less than a constant depending on n times k plus cn times k over m, and this is quite good here because this is exactly the term coming in the Weil law, in fact, of the spectrum. So it's, in some sense, this exponent is optimal. Same thing if the Ricci curvature is or 0, you have something which depends. We have no term, no first term, but again, it is possible to show that there exists manifold eigenvalue and with first non-zero eigenvalue not too small. But it's not easy it's much less easy to construct. I wanted to precisely, I gave two results with curvature. And so when you look at in the first, if you look at the beginning of the theory, so to say, it was a lot of result where the curvature was present, and it's quite obvious that if you are interested in lower bound, it's almost necessary to introduce a bound on curvature, because if you don't do this, locally you can construct some small deformation of the manifold, and you can produce as many small eigenvalues as you wish. So you need to say something. But intuitively, you see that it's not the same for if you are looking at upper bound. If you have, say, a manifold with a spectrum, say 1, 2, 3, 4, etc. If you do a small deformation of the geometry, it will not change. It will not affect. This eigenvalue will not disappear suddenly. So we can hope to have some result constants which are maybe more robust than the curvature, or maybe some result without curvature. And such a result exists for the Laplacian. This is a result by Berger. He gives an estimate, a low bound for the first eigenvalue with respect to the volume and to the injectivity radius of the manifold. And at the same time, by Croke, for all the eigenvalue with respect to the volume of the manifold and the convexity radius. And of course, because it's for the case eigenvalue, you need to have to take into account the. So I just recall, for those who don't know very well the geometry, I like to do picture when I speak from injectivity radius. The injectivity radius, my picture are quite poor, but okay, it's like this. When you look at the surface, of course, if you take a point and if you look a ball of a small radius, this is a topological ball. But if you think to the cylinder, I draw, this is a cylinder and this is a ball, but the center of the ball is behind the cylinder. So if the radius is small enough, you see this is part of the ball. But if I take a radius larger and larger, suddenly the ball is no longer embedded. So the injectivity radius at this point, it is the maximal radius, so that the ball is embedded. And you see that here the injectivity radius is quite large. Here it is quite small. And so the injectivity radius of the manifolds is the minimum of the injectivity radius. The convexity radius is just because when you take a ball in a manifold, embedded in a manifold, it is not necessarily convex. But if you take the radius small enough, it is convex, and this corresponds to the convexity radius. So there is this result in function of this invariant. Now I move to the case of the Steklov eigenvalue, and first I will try to give a result which is a little like the result by Croke. So I take a compact manifold with boundary sigma. Sigma, it may be more than one boundary component. So I write by sigma 1 until sigma b the connected component. If I have 2 points on the manifold, I can consider the usual Riemannian distance between these 2 points. It is you look at all curves between these 2 points and you take the minimum or the infimum of the length of these curves. So this is corresponds to the shortest curves, in fact, between these 2 points. But now, if I take 2 points on the boundary, of course, I can take the distance inside the manifold, but I can also take the distance in the boundary. One speak here from extrinsic distance and here from intrinsic distance. They are not the same in general. Extrinsic distance is less or equal the extrinsic distance is less or equal the intrinsic distance. And there is also the extrinsic or intrinsic diameter. That is the extrinsic diameter is the supremum of the distance between 2 points. So again, this will be very important. So you can draw this. You can do this with a piece of paper. If I take a piece of paper like this, of course, the intrinsic distance will be equal to the extrinsic distance. But now, if the piece of paper becomes like this, you see that between this is my finger, the extrinsic distance is very short, and on the manifold, the intrinsic distance does not change. So I also explain this of this picture because I will use again this picture. So if I have 2 points, I can draw curves inside the boundary, or I can use curve outside the boundary, and this may be much shorter than this. And this is what I speak when I speak from the position of the boundary into the manifold. Is precisely the difference between these two. And with this, you see, this is a result with what I didn't tell. This is what I explained. This is a result with Alexandre Girouard. So we get this result, which looks a little like the result by Croke and Berger. So the volume of the manifold is there, the injectivity reduced to the power d, k to the power d plus 1. There is only a new fact, a new quantities, the diameter, the extrinsic diameter of the boundary, which come into the inequality. So, of course, when you use, as we do, geometric method, you cannot hope to have a sharp inequality in the sense where there are equality cases, for example. It's certainly not the right method to do this, but a very natural question is to ask if all the quantity coming in the inequality have to be there. That is, could we maybe use something, suppress one of these terms? It's not the case, and I will explain why, and it shows that in this sense the inequality is quite good. So the question is, why do we need really all this term of on this inequality? And so this is the opportunity to speak from different kind of example, construction of eigenvalue for the Steklov spectrum. So the different term of the inequality, there is a volume. So for the volume has to be there because there is a general construction by Alexandre Girouard and myself. You begin with a Riemannian manifold with boundary. You can always deform it conformally inside the manifold without touching the boundary, such that the volume goes to infinity and the first eigenvalue for the Steklov goes also to infinity. So I draw a picture. You begin with a manifold with boundary omega g. You want to construct a deformation of this metric, a conformal deformation of this metric. You do like this. You consider the 2 epsilon tubular neighborhood. On the epsilon tubular neighborhood, you will choose h equal to 1 so that the geometry of the boundary does not change. But outside the 2 epsilon neighborhood, you take h epsilon equal 1 over epsilon, which is, of course, you multiply by a very large constant as epsilon goes to 0. And in between, you just glue, you interpolate. So when you do this, of course, the volume goes to infinity. We can show it's not trivial. It's not a surprise when you look at the Rayleigh quotient. There is something to show. Sigma 1 goes to infinity. The injectivity radius, of course, because this is the injectivity radius of the boundary, it does not change. The boundary is fixed, and it's not difficult to show that the extrinsic diameter of the boundary does not change a lot. So this is an example to show that you need to take the volume of omega into account. For the injectivity radius, it's a little more delicate. There are specific examples, but there is a family of examples by Jacques Brisson, who is in the audience, I think, which go like this. She obtained this is example by she exhausts the tubular neighborhood of a manifold, a submanifold of a compact Riemannian manifold, and the best is to explain this on a picture. So you begin with a Riemannian manifold of dimension d+1 greater or equal to 3. You look at the submanifold of codimension at least 2, so here I just take S1. And you consider the epsilon tubular neighborhood, and you let epsilon goes to 0. So she can prove that in this case, so the manifold with boundaries that you consider is the complement of this tubular neighborhood. The boundary of omega epsilon is the boundary of the tubular neighborhood. And what is not obvious a priori is that when you do this, the first eigenvalue of the Steklov goes to infinity, and she can tell much more, but it's enough for my example. It goes to infinity. And you see that the volume of the manifold omega epsilon is not constant, but it goes to the volume of M. The intrinsic diameter of the tubular neighborhood of the boundary, it is more or less the intrinsic diameter of the circle. but the injectivity radius, of course, this is a cylinder, a very small cylinder, and the injectivity radius of a very thin cylinder goes to, and so you see that you need to take into account the injectivity radius. So the last quantity, it is the extrinsic diameter, which was not present in the result by Croke. And in fact, you need to take this into account. So there are a family of examples in a very specific situation by Donato Cianci and Alexandre Girouard. So this is much more specific and also more difficult to explain. So I did a very symbolic picture to try to explain this. So about the exponent, of course, K has to be there, but we don't know if D plus 1 is, I don't think it's optimal. So I come back to the example by Cianci and Girouard. So this is a very symbolic picture. You see, it's a ball of dimension 2n plus 2 on even dimension. So what is important is that a ball of even dimension is foliated. The boundary is a sphere of odd dimension, and you have a foliation of a ball by a sphere. And now, when you have a sphere of odd dimension, it's possible to do a very interesting construction. You can use the fact that there is a natural S1 action of S2n plus 1 and deform the geometry in the direction of the action. And so you can construct family of metric on the sphere with volume 1 and injectivity radius going to 0, which is a priori surprising, but so the curvature goes to minus infinity. And this is a way to construct a large eigenvalue for the Laplacian with a manifold of volume 1. And so what they did, they took an epsilon tubular neighborhood. In the epsilon tubular neighborhood, they don't change anything, so the boundary is invariant. In particular, the injectivity radius of the boundary does not change. But as soon after epsilon or 2 epsilon, they do this terrible construction so that they got a manifold of volume around 1. And the difficulties of the problem is to show that the first eigenvalue for the Steklov goes to infinity. This is a part of the example which is not easy to show. And when you have this, it shows that you need, now if I come back to my inequality, so you need also to have the intrinsic diameter, because the extrinsic diameter, because the other eigenvalue are, yes, I didn't explain very well why is, you see, the volume is around 1, the injectivity radius is fixed, and the diameter, the extrinsic diameter goes to 0, and also sigma 1, so that you need to take into account this diameter. So I didn't explain why it goes very well, why it goes to 0. Come back. So why the diameter goes to 0? You take 2 points, opposite point on the sphere, which are very far. If you go along the geodesic of the sphere, the distance is like pi. But why the extrinsic diameter is small? Because you go at a distance epsilon here. At the other side, you go at a distance epsilon. Now you are in a sphere of diameter going to 0. And so you see that when you do this, then you can, in a very short, there is a very short way here, which allows along this sphere of diameter almost 0, and you go here. So that's in fact, the intrinsic diameter of the boundary does not change, but the extrinsic diameter changes drastically, it goes to 0. So we have seen that all these quantities were useful in this inequality. It's interesting to say that from this estimate for the Steklov problem, one can deduce an estimate for the Laplace spectrum. how can we do? I can come back to my initial example. My initial example of a product, it was a relation between the Steklov spectrum and the Laplace spectrum. So if we know something about the Laplace spectrum, we have information about the Steklov spectrum, but the converse is true also. And if you remember, I told that for L small enough, you know exactly the spectrum of the product. The case eigenvalue is exactly this number. But now we have an inequality for sigma k. So I write this inequality. There is this number is sigma k, which is less than this number of the inequality. But now I have a product. So that, for example, the extrinsic diameter in a product, this is the intrinsic diameter, this is the diameter of sigma. The injectivity radius, this is the injectivity radius of the boundary. And the volume of omega for a product, it's easy to see that is the volume of sigma times the length. So you have L of both sides, you can divide by L and take the limit as L goes to 0. You see that tangent hyperbolic of square root lambda KL divided by L goes to square root of lambda K. And at the end of the story, you get this, you get this inequality, so that you disappear of the game and you have an estimate for the Laplacian coming from the estimate on the Steklov problem. So you see, it's a little different from the result by Croke, because there is so volume, there is injectivity radius. For Croke, it was a convexity radius, but it's the same type of result, but there is the diameter. And so what we can see is that our result implies the result of Berger and Croke, but it's a little better if the diameter becomes large. You see, if the diameter becomes large, you have a better upper bound for lambda. And one can see this with an example. If I take now as manifold, I take of the boundary, I take a circle of length L times, for example, a sphere. So if I take this for sigma, the lambda, you see that this is a product, so lambda 1 is like 1 over L square. The volume of this manifold is L times, and the injectivity radius and convexity radius are bounded below. So the estimate of Berger and Croke diverge as L goes to infinity. The volume divided by the injectivity radius goes to infinity. But if you look in our estimate with the diameter, because of the presence of the diameter, we get this, it goes to 0, like 1 over L. So you see that it's very good because it gives it shows that it goes to 0, but it's not optimal in the sense that here we have 1 over L and here this is 1 over L squared. So this was for the first inequality. And I will to move to another estimate. The time, yes. Just to introduce a couple of notation. If I have a point on omega, again, I can consider the ball with respect to the extrinsic distance d omega. If I take a ball, a point on the boundary, I can also I can, of course, consider the ball with respect to the distance here, omega, but I can also consider the ball with respect to the intrinsic distance on the boundary, the same as before. And I have to introduce two constants, which we use very often, in fact, when we are doing a metric approach of upper bound, but which are maybe a little new for some of you. I will try to explain a little about this. As I told, one can, it's not, we can imagine that the bound on the Ricci curvatures, it was used for the first result I gave in the case of the Laplacian. For upper bound, when you look at the proof, most of the time, the Ricci curvature is used in order to control the growth of ball. And sometimes you have to control the growth of ball. And of course, if you have a lower bound on the Ricci curvature because of the Bishop-Gromov theorem, you can control the growth of ball. But most of the time, it's enough to control the growth of ball. It's not crucial to have the control of the Ricci curvature. So in fact, it was probably introduced in a paper by Grigorian and Netrusov-Yao almost 20 years ago. It's better sometimes when you have a compact manifold like sigma J here, sigma J is one of the boundary components. You can just introduce the growth constant, that is a number which controls the constant of the volume of the ball. Of course, it's maybe very large, but because sigma J is compact, there exists such a constant, and the package it has to do with the measure. And there is another constant which looks similar, which has to do more with the distance. When you have a ball of reduced air, it's clear that it's possible to cover this ball of reduced air with a certain number of points, but maybe this number may be very large, and there is a constant which you can introduce a constant which allow you to control this number. So when you see in the result, when you see I and n, it takes the place of the curvature, so to say, but there are much more robust constants. For example, maybe if I can give you an example where it's better to use such constants than to control the curvature. It's you think to a lattice, to the Z2 lattice. And when you can draw a surface modelized on this Z2 lattice, like with Lego, you take a fundamental piece and you construct a periodic surface, which is like the Z2 lattice. It's clear that you cannot do this. When you do this, you need to have some negative curvature. You cannot do it with positively curved metric. But however, when you think to a surface which is modelized on the Z2 lattice, it's the behavior of ball is Euclidean. That is, for example, the volume, the area of a ball of reduced air, this is a constant time r square and not exponential of the radius as in the hyperbolic space. But if you want to use the Bishop-Gromov, because there are some negative curvature, you cannot do better than an exponential. So sometimes it's very useful to introduce such constant. There is the distortion also. I was always speaking in some sense of the distortion of the boundary, the position of the boundary in the manifold. So I recall I had introduced these two distances, d omega and d sigma, and the extrinsic distance is less or equal to the intrinsic distance. It means that the ball for the intrinsic metric is contained in the ball for the intrinsic distance. And so, but you can ask, is less or equal? Okay, but maybe it is very different or not too different. So the distortion, this measures the difference between these two distances. Exactly like this is a constant, so that this distance is less than a constant times d omega. So I come back to my picture. You can always compare the distance between 2 points on the boundary and inside the manifold. And if, for example, in a situation you take a product, if the boundary is totally geodesic, these two distances are the same, but it may be a situation. For example, it was what I do with my piece of papers. It could be some situation where these two distances are completely different. So the distortion is very big, and this plays a role on on the spectrum of the Steklov. Now, with this new constant, we get this result, which looks quite tricky because there is a lot of quantities in this result, but you can look which are the quantities. Of course, k to some power. There is the volume of the manifold. The volume, here it's a result with respect to one connected component of the boundary, so its volume play a role. This is the distortion will play a role, and there is this term which is ersatz of curvature, if you wish. What is interesting to mention is that the exponent is optimal, which is not clear because the very low for the Steklov, this is in 1/d. So we could hope to do better than 2/d. It's not the case. It's not possible to get better. If we want to have a result with respect to the volume of the whole boundary, it's very similar. You can introduce here the whole boundary, but you need to take into account the number of connected components. It's more or less the same thing. It's not the important fact. And so, as before, this estimate is certainly not sharp in the sense that it's hopeless to have an equality case, but one may ask if the different quantities in the inequality have really to be there. And so I will pass in review this different quantity, but part of the job is already done. For example, the volume, it's exactly the same example as above, that is the conformal deformation inside the manifold. I can take exactly the same. For the volume of the boundary, it has to be large enough in some sense. If it is too small, it gives a very bad estimate a priori. Is it true? Yes, it's the same example as before by Jacques Brisson, because if I recall the example, when you have a tubular neighborhood, of course, the injectivity radius was very small, but also the volume of an epsilon tubular neighborhood is also very small. It goes to 0. And so it's exactly the same example. For the distortion, this is again the example by Chianci and Girouard. I have just here to say that it affects also the constant, the packing constant, and we do such a deformation. The new thing now, there is a number of connected components if you want to take all the different components into account. So there are examples by Alexandre Girouard and myself of a surface with normalized eigenvalue going to infinity and arbitrarily large number of boundary components, and with distortion 1 because locally it's near the boundary you have a product. So this example shows that you need to take the number of connected components of the boundary into account. Less clear is the packing constant, the Croke constant, and the question of the exponent of the boundary. So we can use the same idea as before. That is, you take a manifold sigma, a Riemannian manifold sigma without boundary, and you take the cylinder, omega L, equals 0L times sigma, and you do exactly the same as before. If L is small enough, we know exactly what is the spectrum of Steklov. This is equal to the first eigen, which is we have this expression with respect to the Laplace spectrum. And so you do the same and you get the following. That lambda k of sigma is less than this family, this number here. So because you have a product, the n and r are are fixed, the distortion is just 1. And you see, when you have this inequality, it shows that the exponent cannot be better than 2 over d, because for the manifold sigma of dimension d, you have a very low, and the very low is in k over sigma to the power 2 over d. So you cannot, in fact, do better. And the same example, I can rewrite it in another way. If I rewrite the example like this, so this is the normalized eigenvalue for the Laplacian. You have just to take to k equal to 1. This is less a constant. The distortion is 1. And so if this number is bounded, there is a problem, because on any manifold of dimension higher or equal to 3, you can construct a metric with lambda 1 times a sigma arbitrarily large. And so this is impossible if these numbers stay bound. So you have to take into account this number in the inequality. I think I have a couple of minutes, and I will try to give an idea of the proof of the first result that I recall here, to show you the type of geometrical methods that we use. So the point is we want to get to construct an upper bound for the case eigenvalue, and as I told, we use the min-max. And the idea is to choose a good subspace of dimension k plus 1. And in fact, it's good to take a subspace generated by some k plus 1 function. And it's even better to choose a disjointly supported function, because if they are disjointly supported, it's very easy to see that the maximum of R of u for u in this space generated by this this function, this is just the maximum of the Rayleigh quotient. That you have just to control the different the Rayleigh quotient of the functions that you introduce in the game. You have not to look at linear combination. And so I explain in a picture what type of function we will use. The idea is always the same. You construct the support of the function before to give the function. So here it's particularly simple in this theorem. It's a ball. We will play with ball. You take a ball, you take a point on the boundary, you take a ball of radius r, in green, a ball of radius 2r in orange, and in blue is what is outside this ball of radius 2r. And so you look, you take a function which is 1 in the ball of radius r in the green part, and 0 in the blue part outside of the ball of radius 2r. And you hope that the Rayleigh quotient of this function will be nice enough to give you a nice upper bound. So you have to look a little at the Rayleigh quotient to see where the problems are. One problem is that there is a gradient. The function, it has to go from 1 to 0. It goes proportionally to the distance. So you see that if the radius is too small, the gradient will be very large. But if the radius is too large, the ball will not be disjointly supported. So you have to take something in the middle, so to say. Another gradient is you integrate on omega. So, but the gradient, in fact, it is 0 in the blue part, 0 in the green part, and this is only the orange part that there is something. However, you don't know a little about the geometry. The unique information you have on the geometry of omega is the volume. But the volume of a manifold can be completely concentrated in a region. So you have to deal with this. What occurs if all the volume of omega is in a region? It's bad. The last point is the denominators. So the denominators, it has to be large enough. If you see, the function is 1 here on this ball. But imagine that the volume, if the volume is too small, you will divide by something very small, and so it could be bad. So there are three difficulties. So you do like this. I have to explain how to construct this function. So of course because the diameter of the extrinsic diameter will play a role. We'll introduce it. I pose delta equal to this extrinsic diameter of the boundary component of the connected component of the boundaries that I consider. I take 2 points realizing the diameter, and I draw a curve. I write a geodesics. I draw a curve between P and Q, and along this 2 points, I take 2k plus 2 points which are far enough. So if again I always prefer to draw a picture. So I have these 2 points which are as distance delta. I want to construct 2k plus 2 points, so I can hope it's reasonable to hope that you can have that the distance between each point is at least delta over 4k. This is what we do. And so you have, in fact, this point will be the center of 2k plus 2 ball. That is potential support. So why 2k plus 2 and not k plus 1? Because it's because of this question here of the orange part. The metric can be concentrated in this ball, but when you have 2k plus 2 ball, the metric cannot be concentrated everywhere. So you can always choose k plus 1 of this ball of center xi and reduce delta over 8k, so that the volume of this ball is not too large. That is with respect to the volume of omega and the volume of nk, that is less than omega over k plus 1. So with this, you solve the problem of the possible concentration of the metric. Then you have to, as I told, you have to take into account the gradients. But the distance now, the function will be like this. This is the same picture, but the radius is now delta over 16k. So this distance here is like delta over 16k. So it gives to you what is the gradient to the square. This is 16k divided by delta to the square. So when you introduce this in the Melee quotient, now you have this estimate. On the numerators, you cannot do better. And you are unhappy always because of the denominators where it can be small. So you have to be sure that the volume of this ball is not too small. And you remember that the ball of the intrinsic ball is contained inside the extrinsic ball. And in particular, the volume of this ball here is larger than the volume of the intrinsic ball. So if I can control the volume of this ball, I am done. And it turns out that this is a result of Croke, at least if the injectivity radius, if the radius is small enough, you have an information about the volume of the ball. For small radius, the volume of the ball is a universal constant times the radius to the power d. So a small ball, the volume of a ball of radius small enough is not very small in some sense. And so, of course, this is only for small radius, of course. And so we have to say something for a ball of radius between the injectivity radius and delta. And so you just say, well, R is just greater than the injectivity radius over 2. And so you just say that this is the volume is just larger than another constant. I will say for the universal constant, I always write C of D for a constant, but you have just that it is greater than C times the injectivity radius. And you can write this like this, multiplying by RD divided by RD. This is just greater than something like that. And when you put this in the Rayleigh quotient now, IP, because you see you have delta D plus 2, D plus 1 omega, injectivity to the power D. This is exactly what was announced. We have now exactly our inequality, which is metric, which is obtained by geometrical methods.
This is time for questions now. And if you have a question, you can unmute yourself and ask your question directly, or you could also write the question in the chat and I will relay it to you.
From here, where do we go in terms of upper bounds for the eigenvalues of the Steklov problem? It seems that in terms of geometric quantities, we have the quantities that give us the right exponents, the right exponent that follows by ln k, that all of these quantities seem to be necessary. What from here is the next question we should ask about?
I think for the estimate of this type, it's not good for me to propose something else. That is, of course, you can always try to do better. For example, in the sense that, as I say, for example, for the result I proved, it's not clear that the exponent of k is good. Also, there is always a question of the volume of the manifold, because the volume of the manifold is crucial, but in fact, what is crucial is the volume of the manifold close to the boundary. So this is something to be clarified. This is one thing. Another question that I like very much, I have nothing to say about it because it's very recent. It's related to the, in fact, to the paper by Karpukin and Metras. They propose another normalization. You know, they also use with Alex. There are some normalization you are bounded in the conformal class, but you can think to example which are not bounded for this normalization that is with sigma k times the sigma divided by the volume to the what. And for example, the example by Alexandre and Girouard give counterexamples. They are not bounded for this normalization. It's curious to understand this better. That is what it's always the game between the role of the boundary and the role of the inside the manifold, which is always. We did a lot of progress in 10 years, but there are always questions.
Thank you. I think Doreen has a question.
Yeah. Hi, Bruno. So in the Euclidean case, is this giving a bound for the Steklov eigenvalues in terms only of the diameter?
I mean, my last estimate, I think.
So in the Euclidean case, if you can bound the eigenvalues by the diameter only.
That is, I know of course, your result, but
I mean, the power was not good. So mine one, at least.
It's a question, but I don't.
Yeah.
I know that it's a question to discuss the power in your estimate, but so here, if you are in the Euclidean space, because there is one boundary component, we haven't tried to it's a very nice observation. Yeah. But I cannot answer to
Okay.
you.
Thanks.
With the exception to say that I will think to it immediately.
Thanks.
Anyone else wants to ask something or say something?
I should ask a question.
Hello. Yes, Emily.
Hi, Bruno. Could you go forward? I think it was one slide. You showed the bound, okay, maybe a couple. The corresponding bound on the Laplace that you got from thinking about the cylinder with the second bound.
This one?
Yes. So in 3 dimensions, we know that, or dimension 3 and higher, we know that the n cubed a term must be allowed to grow. Can you say anything in dimension 2?
This is in dimension 2. You have a bound with respect to the genus. It's completely different. You cannot construct a large eigenvalue.
Right. And then how does this bound in dimension 2 compare to known bounds?
Oh, I don't think they are.
Are there any special cases in which this is a good bound? for dimensions?
I don't think so, because you see the methods that we used are far from being optimal. So
Right.
When I see what well, there are a lot of people in the audience who know much more than me, but there are results where you give very precise, constant, not depending only on the genius, and I think it's much better than what we could have here.
I think there was someone else who wanted to ask something before.
Yes, may I? Yes. So I have the following question, but what happens that you introduce a new spectral parameter? So for example, you don't study the Laplacian, you study the Helmholtz equation. Laplacian is equal to some mu times the function, yes?
Mm-hmm.
What will be the estimates of the Steklov eigenvalue?
Oh.
Of course, below the first Neumann eigenvalue.
I don't know. I don't know. I have no idea. If you introduce a condition, would be delta u equal lambda u inside the manifold. Your problem, Alexandre. I don't know. Do you know about this? I don't know the answer about this. But maybe you.
No, I mean this is.
We speak of this sometimes together, but it's an interesting question to look at this parameter. But,
so I don't think we have anything to say about this at this moment, but obviously we could ask similar questions, but it's not done. Yeah.
Because this will explode with the Neumann, the first time, Neumann eigenvalue. Then there will be explosion, and then. Okay.
So no answer.
No answer.
If not, let's thank Bruno again. Thank you very much, Bruno, for the talk.